Well, let's see, what are we on? 6.4. So this is section 6.4, logistic regression. And in the bigger scheme of things, what we've seen so far is in terms of variables. So if I talk about my explanatory variable here this way, well, it could either be categorical or it could be numerical. And then my response variable could also be either categorical or numerical. And so we have this, and we started off in chapter 3 with this, and we used the chi-square test of independence. Then we moved to a categorical explanatory variable and a numerical response variable. That was chapter 4, and we used the ANOVA. Then we had chapter 5, where we used regression, linear regression. I'll put that, linear regression. And we had the numerical and numerical. So the only thing we don't have at this point is what might we do if we have a categorical response and numerical explanatory variable. And it's not all of chapter 6, it's just section 6.4, and this is where we look at this thing, logistic regression. Okay, so that's kind of the idea of the 6.4. Now, we're just going to look at categorical variables with 2 levels. Okay, with 2 levels to kind of see what's going on there. One way to think about this is note categorical variables. We could think about this as categorizing based on the explanatory variables. You know, do we want to categorize this as category A, B, C, D? Well, we're just going to use 2 categories, yes or no, pass, fail, something like that. And so let's kind of picture how this might work with data. Right, and we'll just have a single, so we can draw it, and so with a single explanatory variable. You know, maybe we can have a pre-score. Okay, so our project's going to look at just, now our project's not going to be based on real data, but we're going to do something with kind of looking at kidney screening, you know, so for kidney transplants, in general, right, you want those to work, and you don't want to use up precious resources of donated kidneys and time and money and all that for a transplant that's not going to work. And so what you might have is you might have sort of a pre-score, and I'm just going to look at that as some composite score, you know. So, you know, you could have gotten a 1.1, a 2.8, 3.5, you know, and so on. And then with the transplant, you know, what you might keep track of is something like success at 5 years. something along those lines. And, maybe you call us, well, and we'll just use maybe success and failure. So failure, this transplant did not, make it 5 years. This transplant did not, this one did, and so forth. So we can, I'm going to pause it here. Okay, so we have successes, failures at 5 years, say. That seems to be a typical response that they want to check. And so, okay, if we have a lot of this data, then what I could do is I'm going to put 0 there and a 1 there, and that is a, say, a failure, and that's a success. And here we'll put that pre-score. Those are all the things that go into the matching process. So, age of donors, age of patients, blood type things, and all that go in there. Well, and what you might expect is, if we assume the high score is a good thing, people with low scores, what maybe we found is a lot of failures there, and people with very high scores, what we found is a lot of success. Okay, but scores somewhere in the middle, what we find is, something more like this. And so if we were to look at the probability of success, right? So probability of success, oops, there we go. What we would probably do is kind of take any given spot in here and, take the number of successes divided by how many patients fell in here. And as you look at this, probably the type of curve we're going to see is something kind of like this. Okay, and in math we call that a sigmoidal curve. Okay, and so if we have data that kind of look like that, what we'd like to do is do some sort of prediction if possible. Again, because you want to kind of look at their score and try to decide, does it make sense to do this transplant? And possibly the answer is, well, if they've got at least a 50% chance of success, or at least a 60% chance of success, or 40% chance of success, something like that. Hey, let's do it. And if they have a very low chance of success, maybe we shouldn't. And definitely very high chances of success, we probably should. And so we'd like to be able to analyze this much like we've been able to analyze other predictive measures that we have. Well, so let's take a look at this sort of sigmoidal curve. And on Desmos, I plotted something. Now this formula up here in the top left that you see, the P of X, with these exponentials, that turns out to be a sigmoidal curve. Okay, so we probably would like to ask how well our data fit a curve like that, and then once we know that, we could use the A and the B in our formula up there to help us make predictions for any new scores. Okay, now it's we don't know how to do that, right? We know how to fit the BX plus A, but putting this into the exponential and so forth. Now, but it's interesting if you look at what they call the odds ratio. So that's the probability of success over the probability of failure. And down there in the bottom left, you see P of X over 1 minus P of X. Well, P of X is our probability of success, and 1 minus P of X is our probability of failure. Okay, and oh, and I guess I probably skipped ahead a little bit in that, you know, we would like to find A and B, which are look a lot like linear regression, right? Except they're in that exponential. And notice though that, yeah, as we change A and B, we kind of change the basic shape of that sigmoid. You know, it's still a sigmoid, but you know, we can make it steeper or less steep like that, and then changing A, well, there it moves it along the x-axis. So by changing those two things, we could probably fit any given data pretty well. You know, but yeah, we don't know how to do that. We know how to do linear regression, but we don't know how to do it with the exponentials. But now notice, yeah, if we take the P of X over 1 minus P of X, so that's what we call the odds ratio, the probability of success over the probability of failure. And then we take the log of it. So that's what I did with the sigmoidal curve. Now I'll add it in there. Notice that is a straight line. And so that's what we're going to do in this section is we're going to transform our y data so that it should fit a straight line. Okay, so it's a transformation in the y data, and we're hoping it will fit a straight line. So that's the idea when we start doing our slightly more mathy stuff. Now, you know, we'll see this, but we'll set it up in a spreadsheet so we can just get the job done and not have to go through the you know, we don't have to think about the transformation every time. But that's the idea is if, you know, if my data are creating, my probability of success is creating this kind of sigmoidal curve, we can actually transform our data, transform our response variable, and we'll see that in another video. We can transform that data so that then we can use our linear regression. Okay, so that's going to be the idea, is we transform response to use linear regression. And well, if we can do it with one explanatory variable, now what we know is we can do it with many many explanatory variables. And so we can use linear regression / multiple regression. Okay, so that's the idea. Once we transform our data, then we just do the same thing we did in the last module, and then we'll get a model. In order to really read that model, we'll have to transform back, but we can do that, and so we'll call that good for this video.